Today we are going to start our revision lecture. We have many chapters. We are going to go through them very, very quickly. Chapter 1 was speaking about types of foundations. Of course, we don't have here any problems, just differentiation between what is the difference between shallow foundations and deep foundations, and when we can use shallow foundations and when we can use deep foundations, and that's all. So in this lecture or in this chapter, we need to differentiate between the two types, so that in case we get a question which is better for which, then we can know which one to use. Chapter 2 was dedicated for shallow foundation. This is a very important chapter because you may get normal questions and you may get problems, because we have design of shallow foundations. So usually just concentrate on problems that is given here with numbers. It's solved with anything solved. It means that this is a very important problem that you need to understand. Of course, design of a isolated shallow foundations is very straightforward and simple. We said that before that the main issue is to know, do we have a working plain concrete pad, or it is just added as an extra precaution to ensure that you are working in the clean environment, putting your steel and concrete without any contamination with the soil. This is the main role of the plain concrete. In case it is a thin plain concrete, what is the definition of thin plain concrete? It differs from one coat to the other, but we stick to 20 centimeters. Less than 20 centimeters, it's just something additional, extra precaution. More than 20 centimeters, so it is working with you. We take the load of the column divided by the bearing capacity of the soil, so we get the contact area between the carrying part of the footing and the soil. What is this carrying part? If I have a working plain concrete, then it is the contact between the plain concrete and the soil. If the plain concrete is not working, then I will ignore it as if it is not there, and I will concentrate on the RC. And when I finish, I just add the plain concrete all around with the small thickness that is specified, and that's all. To get the L and the B, we are targeting to have a cantilever from this side equal to the cantilever from the other side. How can we do this? We can do this by having the difference between the L and the B of the footing and the plain concrete, of course, the same as the difference between the A and B of the column. In this case, the cantilever from all sides will be the same. Suppose you did not do this, it's not important, because if you have different cantilevers, then you will have to design each cantilever and get the moment. But if I use this approach, then I don't have to design except one cantilever, because the value of the moment here is equal to there, is equal to here, is equal to there. So it is just one case for design. But if you do not do this, it is not wrong, but it will be more expensive, because the cantilever will be longer from one side than the other, so the moment will be increased. That's all. This is how you calculate the moment, and so on. This is the equation of the D. Then we get the T, adding a 7 centimeter cover, and so on. Later we check shear and punching. Usually in the exam, we do not concentrate on checking shear and punching. The checking shear and punching, we have done it in our coursework. So in the exam, I'm not going to test you in mathematics. I'm just testing you in geotechnical engineering. So geotechnical engineering means that you know that you have to check shear, you know that you have to check punching, but I'm not going to ask you to check it in writing in the exam. But just know that you need to check shear and punching. If shear and punching are unsafe, then I increase the depth. When I increase the depth, I increase it by 10 centimeters. Be generous in the increase. Don't increase it by 2 centimeters. Of course, we cannot increase it by very small values. Make it at least 10 centimeters. Why? Because it is not really a waste of money, because when you increase the depth, you decrease the amount of steel, so more or less the cost is not increased. You have done this in your coursework, and you have done a test for what will happen when you calculated the cost of the footing. So you know that the price of steel is considerable. By the way, in your coursework, most of you ignored the full width of the footing. You all worked as if the footing is 1 meter. You remember you asked me why we are using the B to be 1,000. 1,000, this is the width of the 1 meter that we calculated the moment based on. We calculated a moment for a strip of 1 meter. It means that when I calculate the amount of steel, it is also the amount of steel in this 1 meter. Suppose I have a width of 2.5 meters, then the amount of steel should also be multiplied by 2.5. It is not only the amount that was calculated for the 1 meter. This is very, very important for all of us. Okay, so this is all for check of shear and punching. I will just move very. This table is very important for you to understand the difference between having plain concrete less than 20 centimeter or more than 20 centimeter. Okay, so these are important numbers. These are the minimum dimensions of any footing. The minimum dimension of a footing should be 80 centimeter according to the Egyptian code. It means that the minimum footing I would have is 80 by 80 centimeters. The minimum thickness is 40 centimeters. So the minimum footing is 80 by 80 by 40. This is the minimum dimensions of any footing. The minimum cover is 7 centimeters. So it means that the minimum D is 33. I cannot have a D less than 33. Even with calculation, it is 27. I will have to increase it to 33 to add 7 centimeter and get the 40 centimeter T. The minimum area steel is 1.5 D or 5 phi 12 per meter. So usually I use 5. By the way, phi 12 is the minimum. You cannot use phi 10 or phi 8 in footings. That's all. So this is what in this lecture. Now, design of the isolated footing, we've said this is just the example. This is a solved example. So I will just pass it very quickly to go to what I need, which is here. This is, by the way, when I say here 6 phi 18 per meter, it means that 1 meter includes 6 bars. But if I want to know the total number of bars, then I have to multiply this 6 by this width to get the total number of bars. So if I need the cost, then I cannot calculate the cost for 1 meter. I will calculate the cost for the full footing. So this is important. And as I said before, usually in real life, I do not put 6FTC2041 and leave it for people on site to decide how many bars to use and how to put the bars. No, I tell them exactly that in this length from here to there, I say I have 12 bars, 20 bars. I just write the total number of bars in this length. What is important here is the moment, the case of the moment. That's what I want to show. In case I have a moment, as you have seen before, the moments are very, very complicated to solve. It's not the scope of an exam. I cannot ask you in the exam to solve a problem with a footing with a moment. You'll get very complicated numbers and you will do it wrong. Sure, you will make mistakes in the calculation in the limited time of the exam. So it is out of the scope of an exam. But what is within the scope of an exam is the case of permanent moment. Permanent moment means that I have a footing that always have the moment in one direction. Similar to what? A frame like this. If I have a frame like this, if I have a footing here, usually the moment in this side, for this case of loading, it will be like this all the time. So if I want to design, I can eliminate the moment before starting. How to eliminate the moment? Just shift the column opposite to the direction of the moment with a certain distance to induce an opposite moment equal to the original moment. In this case, both moments will cancel each other and I can continue my work without having any moment. So in this case, it is just a similar problem to a normal problem for a footing without any moment. The only difference is that I have a column that is shifted a little bit, so the cantilever from this side will be bigger than the cantilever from the other side. So when I come to design this amount of steel in this direction, I will design based on the bigger cantilever. This is the only difference between, so you have two main differences. The first difference is that I shift the column, and based on this shifting of the column, I will have a bigger cantilever. But all steps are the same, similar to other problems. So this is an important problem. But starting from here, this is just for your info. You may answer a question, just a theoretical question. What will happen if I have a moment? I will have, instead of having a distributed constant load, it will be variable from F minimum from one side to F maximum from the other side. Just your understanding for what we are doing. But all of these, this is the shape of the footing after the shift. This is the center line of the original footing, and this is the center line of the column, and this is the eccentricity. Based on having a moment in this direction, I just shifted the column in the other direction, so I canceled the moment. That's all. The remaining of this lecture, very, very complicated numbers. Of course, I cannot add this to the exam, but these drawings are all for info, so that you know what we are doing in case of having a moment like this. Its effect on the design will be so and so. This is for your info. So in case of having a temporary moment, I cannot shift the column, because if I shift the column, it will be good in one case, but in the other case, it will be double problem, so I don't want this double problem. So I will leave the column in the middle and will design a footing based on having a variable stress below the footing. And of course, I may have moment in one direction, in two directions, more and complication. This is all out of the scope of a 2 hours exam or 3 hours exam. We cannot do this. So this till the end of the lecture. This is how the shape. Of course, the shape of the reinforcement is very important in any footing. So you have to know the shape very good. Okay. Let's continue the drawing and so on. Of course, this is an example for a case of double moment. We have moment in the x direction, moment in the y direction, and I have to do the shift twice. Once in the x direction, once in the y direction to cancel both moments. This is also for info because I will not go into this complication. Of course, it's not a complication because just instead of calculating one eccentricity, you are going to calculate two eccentricities. That's all. This is the only difference. But the cantilever will be maximum from this direction, and also it will be maximum in this direction. So the cantilever. So this is equivalent to two problems superpositioned together. Okay, this ends this part of the lecture. We go to the bearing capacity. Of course, bearing capacity, we said that what is very important in the bearing capacity is the final figure, this final figure. This is important. You should understand it. You should know what is this, because I'm just, all what we have said before is to reach this understanding. What is this understanding? That in case of changing the width of the footing, I have different allowable contact pressure or allowable soil stresses that is the soil can take. How I can calculate this? I can calculate this based on two equations. The first equation is the equation of the bearing capacity, which is similar to the equation of Terzaghi and so on, and the Egyptian code. And I have another equation or another method for calculating the settlement, because in case of checking for the bearing capacity, maybe the footing is safe in bearing capacity, but the footing will settle 10 centimeters. 10 centimeters is a very excessive number compared to the allowed. The allowed is 2.5 centimeters. So it is unsafe in terms of settlement. So I have to check both. So this is what we do. In this lecture, we studied first the equation of the bearing capacity. Where is the equation of the bearing capacity? This is the method of Terzaghi, but we just know it to understand that the Egyptian code is based on Terzaghi's method, so you don't have to memorize this at all. But what is important is this one. This is the equation given in the Egyptian code, and this is the one that we are going to use in our calculation. Lots of factors. You are going to get all of these factors in your exam. Just substitute in the equation, get the allowable according to the width of the footing based on the bearing capacity. Then calculate the other part, just skip all of this, calculate the settlement. What is the settlement in case of, this is the case of the settlement, this is the equation for the settlement. Of course, I may give you this equation, or you may have to understand it, because it's not really an equation. P by A, this is the stress 1 over ES multiplied by H. This is not an equation. This is just a derivation between the for the relation between the stress and the strain. It's not an equation. So whether it's given or not, you have to know it. If the H is not given, you will have to assume that it is equal to twice the B, and you are going to calculate the allowable Q that is corresponding to a settlement of 2.5 centimeter. Get this, compare it to what you have calculated from the other equation for the bearing capacity, use the minimum. So we repeat this many times for different B. I say here 1 meter, 2 meter, 3 meter, 4, 5, 6, and so on. Each time calculate the allowable for shear, which is the bearing capacity failure, and the allowable for settlement, and so on. Each time, suppose you are here, you are going to get this point and this point. Suppose you are there, you are going to get this point and this point, and here this point and this point, and so on. 5, 6, 10 times, any numbers, usually minimum of 3 to 4 times. So based on these 3 to 4 times, I can draw this line and I can draw this curve. Okay, how to use this figure? Suppose this is the optimum case in a very big engineering firm, and they doing a very complex problem. Then I will give you for each footing a graph like this. I will tell you that this is the graph that presents the allowable contact pressure for the soil for this footing. So to use it, you will have first to assume what is the width, because you haven't designed yet, so you don't know what is the width. I will assume, suppose I will assume that the footing width is 3 meters, and then I go, here is 3 meters, I will go up, I will cut this first line, which is the line for the settlement, I will go horizontally, I will get the allowable contact pressure, I will use it as if this is the contact pressure that is given in the geotechnical report. I will take it, divide the load by this value, the load of the column by this value, design the footing, check all the checks that you are going to do, and so on. So you are going to get the dimensions of the footings. Suppose you get the dimension of the footing 4 by 2, and you were assuming that the footing width at the beginning, we said that it is 3. Now it is 2. So I will have to make another iteration, another trial. I will start here with 2, the value of 2 instead of 3, like the first time. I will go from 2 up till this point. I will get a higher value for the contact pressure. I will divide the load again with this higher value, so I will get another area, and so on. I will try to use these iterations till I get the exact number that matches. If I assume a width of 2.5, then I will get something very close to the 2.5. Of course, this is a little bit complicated. We don't do this except in very important projects. But this is how you save money as much as we can. If there is a problem that we need to save every penny or every pound, then we have to do this. Okay, this end this part. We took the other part. Then now we have a lecture called problematic soil. Problematic soil, of course, we don't have any problems. It is problematic, but we don't have any problems in our exam. Just you have to understand the theory. You have to understand what is problematic soil, what are the types of problematic soil. I don't want you to memorize. Don't tell me it is found in so and so. I don't care. It is found in new areas in Egypt, because problematic soil happened a very long time ago because of areas that were flooded, and they stopped to be flooded since building the high dam. So it is found in many new locations, Shuru, Ubur, Madinti, and so on. All of these areas are new areas that were used in the previous maybe 2 or 3 decades, but before that they were not used. So in these areas you may have these types. What are these types? Expansive soil, collapsible soil, soft clay soil. These are the 3 most important in Egypt. but of course there are many others. We have added here another one, which is the sinkholes. It is important in many places outside Egypt, but in Egypt it is there, but it is limited a little bit. So you have just to understand what is problematic soil, what type of footing is important for or useful for each type of problematic soil. Yani, you don't have swelling soil and you tell me that I'm going to use a raft. Swelling soil, the soil wants to increase and you are putting a big raft on top, so you are not giving the soil a chance to increase in volume without affecting your structure. So there are some wrong choices, so you have to know this by heart. Of course, if you hear the lecture for this the recorded lecture, you will find many details. How to find these types of soil, how to define them during site investigation. This is of course important, because in site investigation we use water. So in case I use water, maybe I would affect the problematic soil before getting the sample out. So I have to use, of course, if I can use an equipment without using water as a cooling agent, this would be very good. Or there are many other approaches that we can do. This is just hear the lecture, and that's all what is required. Deep foundations. In deep foundations we have, of course, deep foundation we mean usually piles. Of course, there are many deep foundations, but piles are the most important. What are the different types of pile? Board pile, driven, and so on. What's the difference? Which is better in where? All of these are very important questions for an engineer. When to use deep foundations and when to use shallow foundations. Of course, this is related to what we have said here. This is the same in the lecture of the types of footings. So in the types of footing, we have studied this before. So this is important. Of course, the types of pile according to material is not that much important. That's all. But what is really important in this lecture, of course, how to differentiate between the end bearing and the friction. This is now you should be mastering this point. But what is important is that you have here 4 types of problems. These are very important. The first type, which is the static formula that is given in the Egyptian code. The static formula is used for piles less than 60 centimeters. So this is very important. We have Q ultimate, which is the sum of the Q friction plus the Q bearing. You have to understand what is the term, or the parameters of the bearing, and what is the parameters used in the friction. All of this is given here in this slide, and so on. So this is the first type that you are going to use. Okay, so these are all related. Of course, there are here some important but let's talk this at the end. Some theories that we need to understand, but we'll discuss it after finishing all of these examples. All of these are the tables, the parameters that are used for the same equation. But what I want to go very quickly is this one. This one is the other type. It is used for piles that are larger than 60 centimeter. This is very important. It's a graphical method. How do I use this graphical method? I want to reach this curve. What is this curve? This curve is the loading curve of the pile. If I put load on the pile and I measure the settlement, This is the relation between load and settlement. If I put a load and measure the settlement, I can draw a curve. This curve, instead of having it like a curve, I can do it approximated to these 3 lines, as if I'm having a curve. So how can I reach these 3 lines connected together? These are the summation of two parts. The first part is the part related to the end bearing, and the second part is the part related to the friction. These are 2 separate curves, so I have to draw this first and to draw this later and superposition or sum them together. How to do this? To draw this curve, I need to know this point A. And to draw this curve, I need to know this point B, because if I know A and I know B, I will just connect A to 0 and go horizontally, and the same for B, connect it to 0 and go horizontally. So now I have 2 curves. So the code has given me these 2 points, point A and point B, just giving me the settlement of point A and the settlement of point B, and the load of point A and the load of point B. So the code gave me 4 numbers. So either I give you these 4 numbers and I will tell you, draw these 2 curves, then sum them together and use them, or I will give you this summed chart, the summation. I will not go into all of this hassle. I will just give you this summation curve. That is the same. By the way, this is something out of our exam. If I give you a loading curve for a pile from a normal case, it will be similar to this one. If I just give you a curve, just one curve, not few lines, and I tell you use it, you can use it, because you can apply what we are going to say now for any type of curve, any shape of curve. Okay, what are we going to do with this curve? 2 things. The first thing, I take the maximum where I have the failure, so it means that this is the failure load of the pile. If I take from this failure load a factor of safety, then I get the allowable load. So this is the allowable load that can be carried by the pile. We have another portion. What it is? The settlement. I cannot have my footing to settle very big value. There should be a limiting number. This limiting number may be 2.5, maybe 10 centimeters. In some cases, it will be given to you that the limiting value of settlement is so and so. So I go from this limiting value, go up vertically till I cut this curve in a point, go horizontally to get the load. So this is the load corresponding to the limiting value of settlement. I compare now 2 things. I compare the load that I got from here after dividing it by the factor of safety, compare it to the load that came from the limiting value of settlement. I will take the minimum. If I take the minimum, then this is the minimum geotechnical load that can be carried by this pile, or really it will be carried by the soil, not the pile, because all our parameters are related to soil, not to pile. So it is the load that can be carried by the soil all around the pile to have a safe pile. After I finish this, what should I compare? I should compare what I got with the structural capacity of the pile. Maybe the pile, and this you do with all methods, because once you reached what is the amount of load carried by the soil, then you have to check that the pile itself, suppose I have a pile made of glass and another pile made, or say made of plastic, and a pile or wood, to be correct, a pile made of wood and a pile made of steel. Are they both going to carry the same amount of load? The soil around them will carry the same, but the pile itself cannot carry. Maybe a concrete pile in one soil will carry a specific value. But if I replace this concrete pile with a wooden pile, it will not be able to carry it. Then in this case, the governing value will be the capacity of the section of the pile. So I have to, later when I finish my solution, to check the here is the geotechnical capacity. This is the one that we have just said, but I will have to go, after finishing this, to calculate something called the structural capacity. The structural capacity is equal to the area pile multiplied by FCA of the concrete. If I have FCA, I multiply it by the area to get a value, compare it to the allowable geotechnical capacity that you have calculated based on many cases, and take the smaller. Okay, you need this part very quickly in Arabic so that you can memorize it when you go home. To draw this, these charts. In the example or in the problem, you are going to be given this point A and this point B. Point A represents the friction part of the pile, and point B represents the ultimate base resistance. I mean the base resistance. we'll speak in Arabic. فأنا هيبقى عندي two charts، هديك النقطة A والنقطة B. النقطة A عشان ترسمها أنت محتاج أديك settlement وأديك الكورسبوندينج لود بتاعها. النقطة B بديك settlement برضو بتاعها وبديك الكورسبوندينج لود بتاعها. وانس إن أنت عرفت ده وعرفت ده هتقدر ترسم التو charts. ما رسمت التو charts، اجمع التو تشارتس على بعض. اجمعهم ازاي؟ اجي عند النقطه A واخد الكورسبوندينج ليها هنا، اجمع القيمه دي على القيمه دي احطها هنا. النقطه B اجمع القيمه دي على القيمه دي واحطها هنا. يبقى انا كده عندي البوينت C والبوينت K، اوصل دي بدي بالزيرو وبمشي افقي، اطلع الشارت الجديده، امسح دول من الذاكره خالص. لو اقدر امسحهم باستيكه امسحهم خلاص، يبقى انا شلت دول من الحسبه بتاعتي. يتبقى لي الكيرف ده. طب الكيرف ده اعمل فيه ايه؟ الالتيميت لود اقسمه على الفاكتور اوف سيفتي يديني قيمه. يبقى الالتيميت لود اللي كان هنا هقسمه على الفاكتور اوف سيفتي هيديني قيمه هنا. السيتلمنت اللي هيديها لي الراجل بتاع الاستراكشر، نفترض انها 2.5 سم، اطلع بال 2.5 سم، اقطع التشارت ده في نقطه ولتكن هنا، امشي افقي يديني قيمه جديده. يبقى اصبح عندي قيمه مناظره للفاكتور اوف سيفتي بتاع الالتيميت، وعندي قيمه مناظره للسيتلمنت. اخد الاصغر منهم اخده واستعمله؟ لا، اقارنه بالاستراكشرال كاباسيتي بتاعت البايل. لو كانت الاستراكشرال كاباسيتي اقل يبقى اخد الاستراكشرال كاباسيتي. That's all in Arabic. So now this is a summary of what we have just said before. Structural capacity is just an equation, FCA multiplied by this is the structure FCA multiplied by the area of the pile. This will give me the capacity of the pile as a section itself, as a concrete section or as a steel section or whatever. So I will just calculate the carrying capacity of the pile itself. I will compare them, take the minimum. So this is the second type of calculation. The third type is the dynamic formula, and we said the dynamic formula is very important for driven piles. So the first type, method is for the piles, the board piles that is less than 60. The second method is for the board pile that is more than 60 centimeters. The third type is mainly for the driven piles. Of course, any one of them can be used for the other, but with some modifications. But this is the main. This formula was driven mainly for, or were presented mainly for the driven piles. If I need to calculate something for the board pile, then I will have to take the number divided by 2 according to the Egyptian code. I can just divide it by 2 to get the number. How is this method used? This is the equation. there is n, something called n bar. I will calculate n, and I will calculate n bar, multiply it by just some parameters of the pile, R and L of the pile. I will get the Q allowable. Take into consideration that this equation gives you Q allowable directly. You don't need to divide by 2.5 or the factor of safety. It is already factorized. This is the allowable load. The opposite, if I tell you what is the ultimate, then you have to multiply it by the factor of safety. So this is something, this is very straightforward. If you see the equation, the example, it will be very, very straightforward. You don't have to, this is an example. This is the presentation for the n values, how to calculate n, how to calculate n bar, then just a normal substitution in the equation. Of course, in this equation, you find that I multiplied by 0.5. Why? Because in this, it was said that use it for board pile, and the equation is for driven pile, so I multiply by 0.5. But if I tell you use it for driven pile, then use it for driven pile, don't multiply by 0.5. How to calculate n, how to calculate n bar? N is the value of the n values here at the pile tip, but not just at the pile tip. I go down D and I go up 3D, which is the diameter, 3 diameters of the pile. Any values given here, I will take the average of them. Here, by chance, it was just one value. Suppose I have here 21, and I have another value here, which is 20. Then if I tell you what is the value of n, it will not be 21, it will not be 20, it will be the average of 21 and 20, so it will be 20.5. This is the value of n. The value of n bar is the sum, or is the average of all of these values starting from pile top to pile end. Exactly. Any values in between will be taken. Here I have 9 values, so I sum the 9 values, divide them by 9, then this will be the n bar, and then normal substitution in the equation. Suppose I finish this, this will be what? This will be the Q allowable of the pile. If I want to compare it to other thing, what would I compare it to? I will compare it to the structural capacity of the pile, of course, because this is all geotechnical capacity. This is what, because I'm using what? I'm using SPT. SPT is something related to soil. So this is what the soil can carry around the pile. But what will the pile carry? Then I will have to divide, to check the structural capacity of the pile. Now we finished the 3 types of course, there is something here called vertical tension. Of course, I can calculate the load for compression and I can calculate the load for tension. What is the difference between compression and tension? Compression, it means that I will calculate the part of the friction and the part of the end bearing. But if I have tension, I don't have end bearing in case of tension, because if I'm pulling the pile outside, then the tension is not working, but the friction is working. So if I tell you calculate the capacity of the pile in tension, then it means that ignore the part for the end bearing. But because I lost a big part in the end bearing, I will give you something as a little bit of compensation at the own weight of the pile. So take here, if I tell you what is the T, which is the tension force, the allowable, I will take the ultimate divided by a factor of safety. But this ultimate, it will be the ultimate based on friction only. Then I will add the own weight without any factorization, without any factor of safety. What is the own weight of the pile? The volume of the pile multiplied by the concrete, the unit weight of concrete. That's all. I added, it will be a considerable part. It will not be a very big part, but it will help a little bit because the own weight is there. It will help in preventing the pile from being tensioned to the top. So this is the case of the tension. This is the normal example. Here is the, of course, you just have to read this, what is pile load test. Of course, you have studied now many equations for the design of piles. Which one to use in real life? Which is better? Which is, you will find that there is very big variations. Of course, this is why in the coursework I told you, try to use a pile 60 centimeter to use both methods and compare. If you compare, you will find that each one gave a different value. So which one to use? Use any one, but at the end, do a clarification for this load or a verification for this load by a pile load test. So pile load test is very important. Just read this. This is normal. How to arrange piles in a pile cap. Yani this is. Of course, it is important if I give you something like this, but this in case I'm speaking about group. Here the efficiency of piles. If I have 5 piles, each pile carrying 100 ton, what is the maximum load that can be carried by these 5 piles? It is, I said one pile carry 100, so the maximum is 500. But will the group carry 500? No, it will not carry 500. It may carry 450 or 400. Why? Because there is an efficiency for the group, and you have to remember the swimming pool example, because friction is resembles using your hand in swimming, and bearing resembles using your legs in swimming. If you are swimming alone, you can use your hands and legs freely. But if you are crowded with your friends all around you, your hands will not be able to work as efficient as before, so you will lose part of your swimming capacity. So you will have to reduce a little. Now we'll go to the third type, or the fourth type of questions or problems, which is very important, is the settlement of the pile groups. Now you can calculate the capacity of each pile, and you can calculate the capacity of the group based on the efficiency of the group. But this is a capacity. What about the settlement? Settlement is very important. How to calculate the settlement? Calculating the settlement is based on removing the piles and putting an imaginary footing instead of these piles. Where is this imaginary footing? In case piles that are mainly end bearing, then this will be it's not mainly sand, but if I have a pile that is mainly end bearing, then I will have the imaginary footing here. If I have piles that are mainly friction, like piles in clay, they are mainly friction, so I will put the imaginary footing at the bottom third of the length of the pile. So this will be the place where I put my footing here, and this will be the place where I put my footing here. What about the piles? Ignore the piles. Delete the piles from your mind. You don't see piles now. You only see a footing here and a footing there. This footing have a compressible layer below it. What is the thickness of this compressible layer from this point to this point? Here the thickness is from this point to this point. Calculate the settlement of this compressible layer, as if you are solving a settlement of a shallow foundation. A shallow foundation, either I give you the edge, because I give you the end of the compressible layer, or if I don't give you the edge, you will assume it to be twice this dimension. Which dimension? The smaller dimension, twice the B. Usually the compressible layer, if I don't have a limit for the top and the bottom of it, if it is extended to whatever, I don't know, then I can take only twice the smaller dimension. If I have a footing here, suppose that this is 3 meters and in the other direction it is 2 meters, then what will be the edge? It will be 2 meters by 2. Okay, so now this, as we said, this is the imaginary footing in both cases. Calculate the settlement. Calculating the settlement. This is our equation for the settlement. This is a derivation for the equation. Usually I tell you just memorize this equation, but it really it's not a memorization. It is the E, which is the stress by the strain. What is the stress? P over A. What is the strain? Delta H by H, and so on. Substitute this. This is your equation. Anyway, I may give you the equation. I may give you may present the equation. It's the same. Delta H is the additional stress coming from the piles from the column. This column, this load divided by the area, it will give you no, I'm sorry, delta H is the settlement. Delta H is the settlement. P over A is the additional stress. P is the load coming from the column. A is the area, this dimension by the perpendicular dimension. So this is P by A, 1 over ES. I have to give you E of the soil, or you have to, as you have done in the coursework, you have to assume a suitable ES multiplied by the thickness of the compressible layer, which is H. In this case, this is H. In this case, this is H. This will give you the settlement of the pile group. This is, of course, an important problem similar to the other three problems. It is not less than them because it is the only way to calculate the settlement that we have studied. This is, but in the other three cases, they are more or less similar to each other, but the settlement, it's only one method. So this is the fourth type, which is the case of the settlement. The other is just a theory. What is a negative skin friction? You have to know it because you may be asked, define what is negative skin friction. Negative skin friction in case of having soft soil, the pile penetrating a soft soil. So I am designing the pile to be carried by the soil. But what really happened in normal life is that the soil, because it is very soft, it will consolidate with time and it will settle, and once it settles, instead of carrying the pile, it will be carried by the pile. So it will be an additional load on the pile, not carrying the pile. So this is very important in case in normal life, in normal design, if I have soft clay, I have to take it into consideration that it is a load on the pile, not a carrying layer for the pile. This is very important. The quality control is very important. As we said before, the pile loading test is very important. Quality control is very important because I do these seismic methods to check the pile from inside. I do it for all piles, not a limited number of piles. All piles I can check because it may tell me if the pile have inclusion, if it have crack, if it have joints, if it have decrease in cross section, increase, anything related to the pile or sometimes related to the soil next to it. They can tell me something like the sonar, the ultrasound that you do when you go to your physician, but we do it on the pile itself. So this is also very important. The last lecture is the lecture for the retaining wall. This was very near, we said it very short time ago. Of course, the beginning is just what are the types of the retaining walls and so on, and how to calculate the active and the passive earth pressure. And we said that we have we are going to use the ranking theory. The ranking theory depends on having two things: K active and K passive, and one of them is K passive is equal to 1 over K passive. So you have to understand, to know the theory, how to calculate K active and K passive. And then this is the equation for the case of active, and this is the equation in case of passive. Once you calculate the K active and K passive, then go to this equation and this equation, one for the active case and one for the passive case. And I will skip the H crack now, but in case of having a soil like this, I will have to apply the equation of the active and the passive at many locations. Where are these locations? First, at the top of the ground and at the bottom of the pipe. This is okay. Then at the beginning of the water table. This is important. And at the interface between any two layers, I have to use it twice. One at the bottom of the upper layer and one at the top of the bottom layer. So these are just at the same depth, maybe 1 centimeter difference between the both, but one using the parameters of the upper soil and one using the parameter of the lower soil. So I apply this for all cases to get the earth pressure. Once I get the earth pressure, I can, here the effect of water, the importance of this example is for the effect of water. I'm showing here water table here and water table at a lower level here. So you have two options. Either you present plus the earth pressure, present a triangle for the water table from this side and another one here for the water table at the other side, or subtract them together to put this case, which is at the beginning it was something like this, starting from 0, going to this point. But what happened is that I removed a triangle from here because this triangle was cancelled by the other triangle that is in the opposite direction. So this example is just to show the effect of groundwater table. Then we check what? We check sliding, we check overturning, and we check bearing capacity. As I said, bearing capacity is out of our scope of the exam. Overturning is within the scope of the exam, but it will be a little bit complicated, so we may a little bit ignore it. What is very important is the sliding case, because it is just simple equations in case we need to design the wall and get the B. But anyway, we are trying to not to go into complicated calculations in the exam. Here is something called the H crack. This is very important because if we apply the equation for the earth pressure at point 1, we will get a negative value. Of course, negative value means that the soil is grabbing the wall or tensioning the wall. Actually, what will happen is that there will be a crack between the wall and the soil. So I will calculate the value here, it will be negative. I calculate the value here, it will be positive. I will draw a line. Then this line will actually start to push the soil will start to push the earth, the wall at this location. So I need to calculate this. Calculate this by drawing, calculate it by whatever trigonometry, whatever you need to calculate, just calculate it. And then once you calculate it, then this will be your only active earth pressure. And here is the passive. Ignore the passive or take the passive, depends on your judgment. And in the exam depend on the text that we are going to come to you in the exam. If the example states ignore the passive, then you have to ignore it. If I take the passive, take the passive. So this is an example for the solved. Just see these 3 examples. They are very important. What is important in the third example is that I just removed this 3.5 meter and told you it is B, design. Give me a design that would satisfy a factor of safety. That's all what is required from you. So usually we do this for a very simple case. No water table, no layers, just one layer, and maybe ignore the passive. I try to minimize all the givens so that you only have simple equations for the B, get the B that would be, say, give you a factor of safety for sliding of 1.3. Substitute for a factor of safety of 1.3, get the B from the equation, and so on. So this is the third example. We were not going to proceed more than this, because starting from here, I started to get very complicated cases of equations that is difficult to solve in an exam. That's all for our lectures for this term, and see you in your graduation ceremony. Thank you.